Hello, everyone. My name is Timur. I'm going to talk about audio in C++. Um, so ACCU were very generous, giving me a 90-minute slot for this, which means that you're going to get actually 2 talks in one. So what I'm going to talk about first is just a motivation why audio is really important, I think. And then the first half of the talk will be how does audio actually work, like at the low level? What's the fundamental things that make it work in software? How do you represent audio in software? How does it work really? And I think if you're, how many people here are actually professional audio developers? All right, so this is going to be for you the really boring half. There's nothing interesting for you there. But then the second half is about a proposal that is currently in the works that I'm one of the authors of, about standardizing some kind of low-level audio functionality for the C++ standard library, and that's going to be the second half of the talk. So yeah, without further ado, let me start with the kind of introduction. So why is audio important? All desktops, all laptops, all phones that you have in your pocket, they all have audio. They have audio input, they have audio output, they have a microphone, they have a speaker. It's something that practically every device these days has. And even embedded devices, like even your microwave, if you push the wrong button, will probably do a beep. So actually, really most devices that run C++ or our computers actually have audio capabilities. So it's one of the fundamental capabilities that computers have. Now, where is audio used? There's so many areas where audio, they're just unthinkable about audio. So without audio. So for example, if you have an interface, a user interface, you click a button, you always have some sound effects going on there that just kind of tell you how to interact with this user interface. Then obviously you have communication software, something like Skype or something else that you use to talk to someone, which obviously needs audio input and output. Then you have multimedia software, something that streams your music from the network, or just plays back a file, or plays back a film, or whatever, and obviously that also needs audio. Games are unthinkable without audio. Do you know any video game that doesn't have any audio effects? That would be a really boring game that probably wouldn't sell very well, right? So, and then obviously there is the professional audio industry, which is kind of what I do, which is software for producing music, for performing music, for composing music, these kinds of things. And then you have creative coding, maybe some installations or ads or whatever, where you have obviously also sound going on, science and research, education, all areas where audio is important. And I would go further and say audio is actually one of the basic forms of human-computer interaction. And let me just kind of demonstrate that with kind of one of the simplest interactive applications that you can really imagine, something like this, which is a computer game from the 70s. Like very, very simple, right? You can implement this in maybe 200 lines of code. What do you need to make this work? You need 3 things. You need to be able to draw on a screen. You need to be able to get some user input through a mouse or a keyboard or a joystick or something like that, and you need sound, right? Those are the 3 things, the 3 basic things that you need. And without them, you cannot even do this, right? We seem to have finally fixed the technical challenges in playing sound. So, as I was saying, you need 3 things to make even the most basic interactive application: graphics, sound, and some kind of user input. And let's see, we're C++ developers, so can we actually make sound with the C++ app today? Yes. Can you tell me how? No, like in standard C++. Yes?
I think you can do a beat noise.
Yes, how do you do that?
Is it like control H or whatever the ASCII code for that is?
No, in code, in standard C++ code.
Oh.
Basically, that's a quiz. Like, write a standard C++ app that makes sound. \A, that's the ASCII bell sound. And I can actually prove to you that this works. So nothing going on here. Oh, let me just copy paste that from here. Copy this in, compile it, make a sound. Oh, sorry. All right. All right. So what I did here is I typed this into an editor, just the code that we just saw, compiled it, and compiled it again, and then played it back. It makes a sound. So you can actually make sound in standard C++. All right, going back to the slides. Unfortunately, this is not quite enough to do this. Because for this, you need at least two different sounds, right? You need one which tells you you hit the ball successfully, and another one which is kind of it went off and like the error sound, basically. So you need at least two sounds, two different ones, to even make this work. Yes?
I'm going to ask, what happens if from two different threads do the bell at the same time and exactly timelessly overlap that, making your multiple sounds?
The question was, what happens if you do this from two different threads simultaneously? And the answer is, I don't know. Let's try it later. So clearly, the capabilities of C++ today are not quite enough to implement this very simple app here. So, but as we all know, people do this stuff. So they write music software, they write communication software, they write games, and a lot of it is done in C++. So you can do it. It turns out modern operating systems all have APIs that let you do that. And on Windows, you have several ones like Wasapi, ASIO, a bunch of deprecated ones. On macOS and iOS, you have Core Audio. On Linux, you have, again, several APIs to choose from. On Android, you also have several libraries. And if you want to do cross-platform stuff, there's also different solutions. And those kind of depend on which industry you're in. Like, for example, very kind of low-level general purpose things are port audio, which is very popular, SDL. Then if you're into games, you probably heard about Fmod. There's a few others. If you're into pro audio, then there's Juice, which is what you would use to write like a synthesizer or a VST plugin. And also, there's dozens of things which are kind of similar to Juice, which other companies like Native Instruments or Ableton or any of these other companies that make pro audio software maintain in-house. So it's kind of, they keep reinventing the wheel in a way. And so the interesting thing is that not all of these are C++. Actually, most of them are not C++. They're either C or Java. The Android ones are Java. Some of the lower level general purpose ones are C. The rest is C++. Core Audio is also C. But at the low level, what actually happens in there is the same. So they offer maybe different higher functionality bits that are kind of more geared towards what you're doing. But at the low level, the actual audio input output, what happens there is the same. And the way you do this has not really changed since the 90s, which is when computers first became fast enough to do real-time audio. So everyone keeps reinventing the wheel, but actually we know how to do this. And why do we have like 50 different ways of doing it? And why is it that if someone asks me, for example, hey, I want to get into audio, I'm a C++ developer. What do I do? Where do I start? And then the answer is, well, it depends. If you want to write a game, you do this. If you're on a Mac, you do that. If you're on Linux, you do this. If you want to do like a synth, then you do this other thing. And there's just no good answer for this. And especially for the kind of low-level stuff, which is really the same everywhere. I think this is really unfortunate because, to quote Bjarne, C++ is there to deal with hardware at a low level and to abstract away from it with zero overhead. And that sounds like audio I/O is pretty much this. So C++ should be really good at doing this. And it's surprising that there's such a fragmented situation that we're in. So I'm talking about low level. So what is this low level? So this first half of the talk is going to be my attempt of kind of summarizing and explaining what actually happens at the low level when you do audio input and output, for example, on your computer. So very basic thing, sound waves, like in the physical world. Essentially, a sound wave is a wave of like varying pressure of air that travels, right? So if you hit an object, then there's going to be vibration that's going to push and pull kind of the air, and then it travels in a wave, and then we humans can detect this. So as the wave of kind of air pressure variance comes into our ear, there is essentially a membrane that vibrates, and then it excites nerve endings in the cochlea, and then those go to signals in our brain. So we talk about basically variations in air pressure that then somehow get converted to some kind of signal. That's essentially what it is. And if you look at microphones, that's exactly the same thing that's going on there. You have a wave of variation in air pressure, and then there is again a membrane, a diaphragm in there which vibrates, and then there's a magnetic coil around it, and then that gets converted via the thing vibrating in the magnetic field induces a current, so that gets converted to an electric current, to an electric signal that then can go into your computer and be converted to a digital signal. And so that's the input. The output is pretty much the same in reverse. If you have a speaker, it's essentially the sound comes in as an electric signal, and then it's just really the opposite thing. You have a coil in there, and then that makes the membrane vibrate, and then that pushes the air, and then you get back to the airwave. So the information here is really kind of this wave, and so we can input it, we can output it. How do we represent this in a computer? Right? So it's a form of data. How do we represent this? So clearly, sound is a signal, right? So it's air pressure, or you can represent it with electric current, you can represent it in whatever other way, but essentially it's some quantity over time, like a scalar quantity over time. It's like the air pressure at this point over time. So how do you represent this in a computer? Very simple way of doing it is you sample it, right? So you just take the value of this continuous signal at certain points in time, you represent them with a number. And one of those numbers is a sample, and that just represents the amplitude at any given time, and that's just literally just a number. This way of doing this is called linear pulse code modulation, or PCM. You might have heard about it. And if you check Wikipedia, you see that it has been around since at least 1926, where someone whose name I forgot used PCM encoding to represent an audio signal, and they were using 5-bit linear PCM. So really, the only thing that has changed since the 1920s is that we have more bits these days. Otherwise, since then, this is basically how you represent audio digitally almost everywhere. There's a few very specialized applications where there are other ways, obviously, to represent an audio signal, like in a low-level kind of hardware driver. It might be that you might have another way of representing them, but for most purposes, this is the way to do it. And so linear PCM, it means the samples are kind of at a regular interval, and you have the sample rate, which is how many samples per second you have. Typical values are 44,000, 48,000, something like that. It has to do with the human ear, so we can hear up to about 20,000 hertz. And then if you sample things like that, then there's a Nyquist theorem that says if you use a sampling frequency f, then you can represent audio frequencies up to f, up to the half of f. So you can represent frequencies up to 20,000 hertz if you use at least 40,000 hertz as the sample rate. And then the other quantity here is the bit depth. Like we already talked about this, how many bits do you use to represent the actual amplitude? Typical values these days are either 16-bit, which is what a CD uses, or you might go up to 24-bit. And this, again, is directly related to human hearing. So 16-bit gives you a dynamic range of about, I think, 96 decibels between like the faintest sound you can represent and the loudest one. 24-bit, I think, gives you 140 decibels. I'm not sure. something around that. And I think the human dynamic range of human hearing is about 120. So like the faintest sound that you can hear with your ear versus the pain threshold of the ear, something around 120 decibels. So this is kind of tuned to the frequencies that our ears can hear and kind of the dynamic range that we can interpret. And if you use these kinds of numbers for sample rate and bit depth, then you can pretty much cover everything that human ear can hear. But obviously, we are doing quantization here, so this is going to have an effect on what you hear. And there's really this nice analogy to graphics, which may be more intuitive to you if you have not done audio stuff before. So here's basically an image that's from a book about core audio of this animal, and then basically if you go to the right, you increase the resolution, and if you go to the top, you increase the bit depth of each pixel, right? How many different shades of white or black do you have? And this is really the same. So basically, this dimension would be the frequency, like the resolution is how many frequencies you can represent, and the other dimension would be the bit depth. And if you go to like low bit depth, you have these kind of artifacts, and you have the same artifacts if you do audio, where if you represent something with 4-bit instead of 16-bit, then you're going to hear quantization noise, and the quality of your signal is going to degrade. So this is how we represent audio. Another thing that is missing here is we have channels, like microphones have 1 channel, maybe this headphone have 2 channels. You might have a surround system that has 6 channels or 8 channels. So this is another thing that we need here. So you might have several of those at the same time. And so like, for example, here you have a signal for the left speaker and a signal for the right speaker. And then there's one other term that we need, which is the frame, which is basically a snapshot in time, like a sample per channel. This is really important to get this terminology right, because some frameworks kind of confuse sample and frame, where they say they mean sample, which is a number, but what they actually mean is a frame, like a number per channel. So it's really important to get the terminology right here. So frame is basically 1 sample per channel. It's like a frame in video, more or less. Like this is kind of the way, like the value of your signal everywhere, all the channels at one point in time. Right, so these channels, they have names. So they're not just numbers, they have names. They can be left, right channel, and so on and so forth. There's different layouts. So if you have 8 output channels, you don't know if it's like 4 stereo output or maybe 7 1 surround. That's extra information that you need to know. Unfortunately, that's not really portable. Like, for example, some operating systems have left, right, and center for like the first 3 channels, and others have left, center, right. So actually the name of the channels kind of carries some extra meaning that you kind of have to know about. And then speaking of devices, you have different devices. So you obviously have input-only devices, which are the microphone, for example. You have output-only devices, which are speakers. You have devices which can do input and output. And if you're a sound engineer, you might have one of those, which is one of those interfaces which might have dozens of inputs and dozens of outputs. And that's what you're going to be working with. And those devices have different properties. One of them is the sample type. So we said a sample is a number. Like, what kind of type do you use to represent that? And on desktop hardware, it's typically a 32-bit float between -1 and 1, which gives you this 24-bit dynamic range. That's a convention that's very, very popular. But also you have other APIs which use 24-bit packed in or other things. And then on phones, especially older ones, you probably would rather have 16-bit integer instead of the 32-bit float. And in an embedded platform, you might even have fixed point numbers or 8-bit integers or other things. And what is used is what is given to you by the API is kind of determined by the API, and the device talks to this API. So this is essentially a setting, and that can change also at runtime. So the sample type, the sample rate, the bit depth, the channel layouts, all the stuff that we have talked about. So it's not just something you can type def out, unfortunately, right? You can't just say, well, on this platform, a sample is a float. It doesn't work like that, because it's something that can actually change at runtime. Then about these devices, so typically there's one device which is kind of the default input, which is maybe the microphone, for example. If you have a laptop, there's one device which is the default output, configured in like the user settings. But then you might have more devices and you might want to switch between them. Like we just did earlier when we tried to figure out where to play the sound from for this presentation. And if you're writing an app, you might want to react to this in different ways. So for example, a simple kind of player would just play back the sound through whatever is currently the default output. Another app, like for example, this is a screenshot of Discord, which is the chat client. And then if you do this kind of thing, you have it open and then you plug in a new device, like if you plug in your headphones, it's going to ask you, hey, there's a new device. Do you want to switch it to it or not? And then a third way of doing it, for example, if you have some complicated pro audio production software, you might want to actually manually choose different devices. And so, and then there's other stuff going on. So you have, so obviously we said like the device configuration can change during runtime, but also the operating system might have global settings on top of that. So for example, on this laptop, you have, global volume up and down setting, and maybe your app wants to interact with this setting too, or some operating systems have like a global pan, like left-right setting, or EQ, OS level mixer, where like all the different apps kind of write their audio output somewhere, and then kind of it all gets mixed together and sent to the output. There's this other way of doing it where, which typically is used in professional audio apps, where you have this exclusive mode, which is kind of the opposite, which is not all the apps send their output to the mixer and then the operating system mixes them together, but you're directly controlling the device and only your app sends audio output to the device. You're kind of bypassing the operating system mixer. So that's something that you want to do maybe if you're in the pro audio world. And then basically, how do you actually do audio I/O? So there's these layers, right? So you have at the very low layer, you have the hardware which actually gets the analog signal from the microphone, for example, and then converts that to digital signal. And then you have a driver which sends that to your the rest of your system. And then you have an operating system which kind of picks that up and makes that available to the user land in some form of device driver API, like Core Audio on Mac, or Wasabi or ASIO on Windows, or ALSA on Linux. And then this is kind of the red line here. This is kind of where audio I/O becomes available to the user space. And then you have one of those APIs that the operating system gives you. And then you can talk to it directly, right? So you can just write a Core Audio app that directly talks to the Core Audio layer. Actually, there's several layers. There's like a HAL, which is like the hardware abstraction layer. It's like super low level. And then there's other APIs which are a bit more high level and yet more high level. So you can choose to talk to any of these API levels, or you can use a middleware, cross-platform middleware layer and talk to that one, something like Juice or Fmod or Port Audio. So yeah, like you can talk to this driver API through any of these different layers, but ultimately that's kind of the thing that you're going to end up talking to. And how does that work? So how do you exchange data with the audio device through this driver API kind of boundary? So the first thing is that you have a sound card, and the sound card has one of those things in it, which is a quartz crystal, which is essentially a timer. So it keeps time, and it's going to call you back through all these layers of operating system stuff. It's going to call you back regularly, and then what you're going to get is you're going to get an audio buffer. We're going to talk about this in a minute in more detail. So at regular time intervals, which are kind of timed by this quartz crystal, you're going to get a callback through all these layers into your application code, and then you're going to get an audio buffer, and then if it's input, you're going to have to do something with this data, or if you're doing output, you're going to get an empty buffer, and you have to write your output into this buffer. And then it's going to be sent to the speakers, and then you're going to get the next callback and the next callback, and it just keeps going and going and going. So what kind of we need to add to this picture where we have samples and frames and channels is the notion of a buffer, which basically is a fixed size chunk So typical numbers are maybe 128 frames or 256 frames. It's again very important to distinguish frames and samples here. So different pieces of software kind of get that mixed up. So you might want to have, for example, you might have 128 frames in a buffer, and then that buffer is essentially a 2D array of numbers, right? So if your sample is a float, which it most of the time is on a desktop, laptop, then you're going to have a 2D array of floats, and one dimension is going to be the channels, and the other dimension is going to be the frames. And that's what a buffer is. And that's the fundamental data type or data chunk that you're going to end up exchanging with the audio device. And then you might have an input buffer and an output buffer, actually. And the buffer size is something that you can actually control. So if you have like very simple audio apps, you might not really care about this. If you're a bit more pro, then you might want to actually be able to set this. So for example, this is a screenshot of Ableton Live. It's a popular audio production software. And there it has the setting. I believe in most operating systems, if you dig down to more advanced control panels, you also have the setting somewhere there. Basically what it is, it's a trade-off between latency and performance, right? So why do we have these buffers in the first place? You could exchange every frame individually, right? But remember that the sample rate is something like 48,000 hertz. So you're going to have 48,000 frames per second. And it's very, very inefficient to do like a callback through all these API layers from the device to your app 48,000 times a second. That's very, very inefficient. There's going to be huge call overhead. So that's not how you do it. So this is the reason we have these buffers. But if you have a very long buffer, like if you have a buffer of like 4,000 frames, then that's going to be a tenth of a second. And that's a lot of time. Like if you it's like 100 milliseconds. That's a delay that the human ear can hear. Like if the sound is offset by 0.1 seconds, then you notice that something's wrong. So you're going to have this long kind of latency. So what you need to choose here is this ideal compromise between, performance, that you don't overload your computer by doing all these calls, but then also not have too long latency that it becomes annoying for the user to use your software. So that's a really important parameter, the buffer size. Actually, it's interesting because here they again say 512 samples, and I'm not sure what they mean. I think they actually mean frames here. I'm pretty sure they actually mean frames. So this is really, really confusing because each frame actually also consists of samples. So again, sample is a single number, frame is a number per channel. And then another thing that we might want to know about this is, so we said a buffer is a 2D array, and you have these two dimensions like channels and frames. How do you order this? And this is actually a thing that also varies from device to device and from API to API. So basically you have two ways of doing it, interleaved and de-interleaved, which are just the audio terms for row major order and column major order, because that's really what it is if you have a 2D matrix. So you can either do interleave, which means this is a frame, and you basically the bigger dimension is kind of the frames, and then the fastest running dimension is the channels. So you're going to have left and right channel for the first frame, left and right channel for the second frame, or you do it the other way around, and you first have all the frames for the first channel in the buffer, and then you have all the frames for the second channel in the buffer. And those are just different ways of ordering it. And the first one is really good if if you're just playing back something maybe and you care about one frame at a time. And then the second one is really good if you want to do things on long chunks of things per channel, like maybe you want to take this and do a FFT on it, or do something, an algorithm that works on one channel at a time. So both of them are useful, and typically, depending on the API that you're using, you're going to get one or the other, and you might want to reorder it. Like for example, on core audio, you typically get an interleaved buffer. If you use Juice, you get a de-interleaved buffer. Depends, but you need to be aware of it. So we talked about devices, callbacks, buffers. So how does it actually look? So this is one of the, I think this is how it looks in Juice if you use one of the ways of doing it there. So you get an audio callback, which means you get some input channel data, which is a pointer to a pointer, which is basically this kind of 2D structure, and how many channels you have. You get output channel data, pointer to pointer, and output channels, and then you get how many frames you have. So here, actually, the terminology is correctly in this case. And then what you get is, if you do audio output, you might want to write some numbers in it. And that's really like this kind of low-level generating audio. So what we're doing here is we're just writing a sine wave into the output buffer, and we ignore the input buffer. So that's maybe the sound that you heard earlier when we were testing things. So this is what happens here. We take the output channel data, and we generate a sine wave. And with stood sine, this is probably not the fastest way to actually do it. Don't do this in Pro Audio, but it works. And we just generate the sine wave, and into every channel we write the next value of this sine wave. So one last thing I want to say about this is that, so we said that we have audio buffers, and then we said that a typical sample rate is something like 48,000 samples per second, and we also said that a good typical size for a buffer is maybe 128 frames. So you can do the math in your head, like how often do you get these callbacks? And it turns out, well, something between every millisecond, every few milliseconds, or even several times per millisecond, but like typically maybe 1-2 milliseconds. So you're gonna get 1,000 of these callbacks per second. And because essentially you're talking directly to the sound card, even though it's through all these API layers, but eventually this buffer is gonna get copied into something that actually gets output to the speakers, or it's actually incoming if it's coming from a microphone. So really, you just have these 2 milliseconds to fill this buffer with audio, or if you're receiving audio, to like copy it out somewhere, because then you're going to get the next callback, and this all data is going to be invalidated, right? And then you're going to have the next buffer. So you only really have this like time of 1 or 2 milliseconds to do all your code that generates everything or writes stuff. And that is typically what we call a near real-time callback. So it's not really strictly real-time, because C++ is not a real-time language, and maybe Windows or Mac OS or Linux are not really real-time operating systems in the sense that you would have on an airplane, for example, because you still have a thread scheduler and things like that. You can still, but it's near real-time, which means it's, for practical purposes, it's a real-time application. So you have this 1 millisecond to successfully write your data that's then going to be sent to the speakers. And the interesting thing is that the human ear is like very sensitive to kind of sudden changes in the kind of smooth audio signal that you're normally hearing. So it means that if you fail to write even one of those samples, like one of those 48,000 numbers per second, if you even miss just one, you're going to have a sudden incontinuity in the signal, and you're going to hear that as an audible glitch or pop. So if you fail to write even one of those numbers, or even worse, you miss a whole buffer, that's a very obvious audio glitch that everyone in the room could hear if I would have the time to recreate this now. So really what it means is that you cannot fail, right? So you cannot not write the buffer, because then it means then that everyone would hear this nasty click or glitch sound. So even if everything goes wrong, you can't just throw an exception and say, hey, I can't do this. You have to at least, fade out. You can't just abruptly stop the signal. You have to do something sensible, but you always have to keep going somehow. And then you can write zeros into the buffer, but you have to kind of fade it out, because otherwise you're again going to get an inconsistency in the signal that you can hear. So you can't really fail. You always have to have a plan B, so to say, even if everything goes wrong. You always have to write valid data out. And because stuff typically happens on a high priority thread that you get from the operating system, then that also means that there's a lot of stuff you cannot do. So you can't use locks mutexes in there, because first of all, you don't know how long it's going to take until you can acquire the lock, and you only have 1 millisecond. But actually, a bigger problem is that even if even if you're guarding even not that much code with the mutex, the moment you wait for something, there's a thread scheduler, right? So it means that even if you're on this high priority thread, but you wait for something, then the thread that you're waiting for typically will be a thread with lower priority, and then you get this thing which is called priority inversion, where the thread scheduler will actually lower the priority of the audio thread, and then everything will become very sad. And the other thing that you cannot do is you can't allocate memory, because that's also a locking operation that has indeterminate time. Like, you don't know how long that's going to take. So Herb in his keynote just before this said, if you want to write code that is guaranteed not to allocate, we need to be very, very careful about how you write such code. Well, guess what? If you write audio code, you have to do that all the time. This is literally the world we live in. And yes, so this is what we have to do here. So you can't use locks, you can't allocate memory, you can't do file I/O, network I/O. All of these things are locking and slow. You can't call any code where you don't know how long it's going to take to finish. Like you really need to be careful about API calls, because maybe they have a lock inside. They're going to call this really slow operating system thing. You don't know, so you can't call this code in the audio callback. So it becomes really important to synchronize all these threads that you have in a lock-free way. So if you want to get any data into the audio thread or out of the audio thread, you need to use lock-free queues, other like lock-free structures, or std atomic if it's just single numbers. So there's all these techniques. I've done a bunch of talks on this stuff. I'm not going to go into this now. But yeah, it's a very kind of peculiar way of writing code. But now, actually, it's really interesting, because if you're a pro audio developer, you know this stuff. This is basically the world you live in. But most people, when I talk to them about audio, and they say, "Hey, cool, you're doing like an audio library," and then I start talking about all the stuff. They're like, "No, I'm not interested in this. This is like, let the experts do this. I don't care about any of this stuff." So what most people actually want, if you talk about functionality in audio, like, okay, here's an audio library. What do you want to do with it? 99% of the people, they just want to do this, right? So they just want to take a sound and play it. And they don't care about how it works. They're like, okay, everything you're talking about now, I don't care about any of the stuff. You're the library implementer. You worry about this. I just want to write this one line of code. If I have a game, I just want to play the beep, when the monster hits the wall, or I don't know. And just like, give me an easy way of doing this. And this is a very, very different problem from kind of the low-level audio I/O problem that I talked about earlier. But actually it turns out that, well, on the one hand, there's a lot of stuff actually that needs to keep happening before you can do this. On the other hand, actually most of it you can do in standard C++. So let's look quickly at what we need to make this work. And there's a bunch of libraries that give you this. So what happens under the hood? So we talked about the audio processing thread, which is essentially a real-time thread. So you have this callback, you need to generate some audio. And then the other thing I didn't talk about is that you have a sample rate, and the sample rate of your file and the sample rate of your device, they might not be the same. So you might want to resample it. And then I also said that audio signals are typically floats between -1 and 1. So you need to make sure that the values are actually between -1 and 1, or things will, again, turn very sad. So you need to clip it, and then you need to write this result into the buffer. So now, what we actually want to do, you want to read a file, and then one big complicated chunk of functionality is there's all these different audio formats. There's WAV, there's MP3, there's all numbers of other formats. Some of them are lossless, some of them are lossy compression. Some of the compression algorithms have a variable bit rate, so you don't even know how much of the file corresponds to how many milliseconds of audio. And you need to actually churn through the data to find that out. And so you need to decode the audio file, which is a whole world in itself I'm not going to talk about. But this is just bit crunching, right? So you have libraries that do all this stuff. And then you want to write this out. So how do you do this? And obviously we can't do this on the audio thread there, because this is file I/O, right? You can't do file I/O on the audio thread, because that's going to block, that's going to potentially be rather slow. So it turns out the typical, easiest, and most common way to connect these is via lock-free buffers. And this is a talk I gave, I think, 2 years ago at this conference, like how do you implement this? So I'm not going to go into that now. But basically what you do is you have a lock-free queue, and then from one thread you kind of push data into it, and then from the other one, the processing thread, you kind of pop it off. So whenever you need to communicate between different threads, and the same would happen in reverse if you want to, like for example, record something from the microphone and write that to the disk. That's the second most common thing that people want after playing back a file. Record a sound, save it into a file. So you have to do the whole thing in reverse. So the only thing you do in the callback is you copy it out to the log-free queue, the log-free buffer, and then you have another thread which actually writes the file and pops it off. But it turns out that even though a lot of the stuff is rather complicated and rather hard to do, there are lots of libraries that are doing this, and actually most of the stuff you can do in standard C++ because it's just number crunching and file I/O, and actually now we even have file I/O in the standard. Since C++ 17, we have set file system. So it turns out the only bit out of this whole machinery that you cannot do in standard C++ today is this bit. Right? This is the only thing that you cannot do in C++ today, for which you need proprietary APIs from Microsoft, Apple, or Linux APIs, which are not standard C++, or you need middleware that kind of is another layer on top of that, but it's not portable, right? It just isn't portable. And that's unfortunate because basically everyone keeps re-implementing this stuff on all these platforms over and over and over again, although it's just this one mechanism which hasn't really changed since decades. So that made me think, well, should we not be able to do this in C++? Like, should that not be a standard C++ facility, just this bit? And so here's some, like, I would say, semi-official guidelines on what belongs in the standard library. So first of all, it should be something that standardizes existing practice. Right? So you're not going to put some brand new experimental thing into the C++ standard library. It should be something that hasn't changed in decades. It's just working. Everyone knows how to do this. So let's just standardize it. And the other thing is there should be clear need for it. So either it should be something that almost every program is likely to use, like vector, or it should be something that cannot be done portably otherwise. So you have to provide a facility in the standard library because you cannot do it, you cannot implement it yourself because the bits that you have to talk to, like your operating system, they are not there. So like file system is the best example. So if you don't have file system, you can't write file system in standard C++. You need to either talk to a kind of native non-standard API, or you have it in the standard library. The third criterion is it could be something that's just very difficult to implement correctly, like shared pointer. If you look at how shared pointer works, that's really hard to get right. Or it should be something that you cannot do without the help of the compiler. And it turns out, well, okay, low-level audio I/O, it clearly falls into this bracket, right? It clearly satisfies all these conditions. And then if you talk about the 4 different types of needs, then I think it also pretty clearly falls into both of these categories. So it encapsulates known portability. It's like file system or network, which is something that we're standardizing now as well. And it's difficult to implement correctly. But it's been done for decades, so there's no magic there. It's just, why don't we just provide this? And again, to call up this quote again, well, C++ is the perfect language to do this. And then I had this idea of like, okay, should we just take this, basically everything that we talked about in the first half of the talk, like this is basically what I think is kind of low-level audio I/O. Should we just take this and write a proposal to put that in the C++ standard library? And I had this idea a couple of years ago, and I was thinking about it, but then it didn't really go anywhere because people have jobs. But the idea was kind of really, we want this. So I've been on the C++ standard committee for about 3 years now, and there I met Guy Davidson, who is here in the room. And Guy Davidson is working on the graphics proposal, which you might have heard about. And we started talking to each other. I was like, hey, your graphics stuff, I'm thinking about doing audio, not really sure if it's worth it, but it feels like those belong to the same kind of category of things. Like you really need graphics, audio, and some kind of user input. And if you have these 3 things, like we saw in the beginning of the talk, then you can actually write apps in C++. And then the guy said, hey, you know what? I'm happy you asked me because I'm just now talking to another guy whose name is also Guy, who has the same idea and who also wants to do this and standardize. Oh, sorry, my battery is actually empty. Does anyone have a MacBook charger? Guy said, hey, I'm talking to this other guy whose name is also Guy, and he's a game audio expert. He literally wrote the book about how to do audio in games. And he's also been thinking about doing this. So maybe we should all talk to each other. And then basically we created this group of, me and the other two guys, and we started talking about this, and then we started actually designing the API. Like, this is the functionality we kind of want to standardize. What would the API look like? So we had this half a year. So this started in April 2018, which was exactly a year ago. And then we had like half a year where we were just designing the API kind of via email, essentially. And it was really beautiful because it turned out that we're not inventing anything new. Like, everything that we're doing is basically everything that all these other frameworks and API that have existed, they do all exactly the same thing, slightly differently. So let's just take the common denominator of this, make it a bit more kind of standard C++-like, or like modern C++-like, and that's our API. And it turned out that a lot of design decisions were actually really easy, because it's like, oh, everyone's doing it like this. Okay, let's do it like this. Or like, okay, so everyone's doing, void star pointer. That's not something you really do in standard C++. So let's just change this to something else and then do that. So we worked like about half a year on this API in between our actual jobs, kind of via email. And then in November last year, we all met at the Audio Developer Conference in London and presented this API. So that was actually really nice. So we got a lot of feedback from pro audio people at this conference. And then we took everything we had. We took all the really, really useful feedback that we got, and we put that, and then we were like, okay, so let's actually propose this for C++. And it turns out, so here's the kind of organizational structure of the C++ committee. It turns out there is actually a subgroup here, which is SG13, which is responsible for human-machine interaction and I/O. And this is the subgroup that is really relevant there. And we asked them kind of, hey, do you want to see an audio proposal? And again, the feedback was, yes, please, write one. This is useful. And SG13 was kind of restarted relatively recently to talk about the graphics proposal. But then right now, the graphics proposal is kind of, I think it's a bit like with this EU membership of this country. It's kind of a bit in limbo. So there's a chance we might get it, but some people don't like it. And then what we actually want is we want them to kind of decide on whether they want it or not, but it's not really clear how to even do that. So I really hope the graphics proposal is going to happen, because as I said earlier, I really think graphics, audio, and user input all belong together. But in the meantime, while graphics is in limbo, they have a lot more time to look at audio, which is great. So what we did is we wrote a proposal, which is the R0, that's the revision number, of proposing an audio API for standard C++, and we brought that to the last committee meeting, C++ committee meeting, which happened in Kona in Hawaii in February. And we presented this proposal there. Hawaii is a beautiful place, but if you go to one of those meetings, you're actually not going to see any of this, because what you're going to see is this. And so whether it's in Hawaii or in Antarctica, it doesn't really matter. Like, you don't notice the difference because you're in one of those windowless, air-conditioned rooms for 6 days. So we went there, we presented this proposal, and then we again got a lot of useful feedback. And people said, yes, this is good. This is like, maybe not, you need to change this here, change there, and then we talk to these other people who also do like a callback thing. So then we took all this very, very useful feedback, and we wrote a revision 1, which is the next version of this audio API, and we published that a month ago. So you can read that current status if you go to this URL. And we have a reference implementation of this R1, which is on GitHub. So you can check this out. It's not 100% correct maybe, because it's really a hobby project of ours, and it's not quite 100% complete yet. And most notably, currently it only works on macOS, because I had time to implement it on Core Audio. But what we really want is we also want it to work on Windows and on Linux. So I think, did you say you wanted to write the Wasapi implementation on Windows? if someone knows about Linux audio and wants to write like an ALSA implementation of it, that would be really great. So this is super useful. Let's talk about this afterwards. So I'm going to use the last half hour that we have to run you through this API that is in this proposal. And then you're going to see that hopefully it's actually not that much. It's actually really just this one bit that is currently not portable. And there's only really two important classes in there, which is the audio buffer, which we discussed. It's essentially this like 2D array structure. How do you represent audio data? And then the audio device, which is the thing that you need to talk to do IO. So audio buffer. So this, again, this is R1, a revision of the proposal. It's not set in stone. It's still not perfect. There's stuff missing. Stuff is going to change. So this is work in progress. So we have currently these size functions, so you can figure out how big the buffer is. And again, terminology is important. So you might want to know the size in frames or in samples or in bytes. I'm not sure if all four of these are necessary, because kind of the size in bytes is just the size in samples times type of size of the size of sample type. So I'm not sure if we need all four of those, but we need at least two and maybe three. And then we have this, which I think in the original version was a data, and it would give you a pointer. That's, I think, what's currently in the paper. Pointer and size is kind of ugly. We have span now in C++20, so what we really want is we want to return a span. And these are just all the samples. And then most of the time you would loop through them either via channel or via frames. So what you really want is you want this access operator, which is like the two-dimensional thing where you give it the frame index and the channel index, and it's going to index into this 2D array. And then there's one complication, is that, as I said, you can have a different sample type. You don't know if that's a float or an int, and it can be interleaved or de-interleaved. So we decided to make these template parameters, and then it becomes this kind of thing where you have an audio basic buffer, and then there's just kind of the reasonable default, which is what 90% of the people are going to be using. So you have this thing templated on the sample type and on the buffer order, and this is really nice because this is one thing. Oh yeah, and these are just kind of tag types. This is really nice because one of the things that we learned in Kona is that there is this type MD-span, which is a multi-dimensional array essentially, which is also being proposed for C++. Unfortunately, it didn't make C++20, but it's almost ready. I think pretty much definitely going to be in C++23. And that's literally the same thing. So we just use it as the underlying data structure for this buffer. So MD-span is basically just this multi-dimensional array, and we say, this is the sample type, which is typically float, and then it has two dimensions, both of which are dynamic, right? So your buffer can have different size, different number of channels, different number of frames. And then the third template argument of MD-span is just whether it's row major or column major, basically. And this is literally exactly the same thing as interleaved or de-interleaved. So we can just use this as the underlying type and just wrap it with like a more kind of audio-friendly kind of adapter API. I should also point out that this is non-owning. So there is obviously the question of whether an audio buffer should be like an owning thing, like a vector, like a 2D vector essentially, or it should be like a non-owning thing, like a 2D span. And there's some frameworks which kind of do both at the same time, and you kind of have to handle this at runtime, and that's unfortunate. So we decided, let's go with the non-owning thing, and you can still write an owning wrapper around it if you want to, but those should really be different types, because you want to know whether it allocates memory if you create one of those or not, and it shouldn't. So this is basically the only data structure that we have in there. This is basically audio data. And then the second class is the device. And the device has relatively straightforward API. It has a name, like what you see in the user settings, which is, speakers, like default microphone or whatever, which is just a string. And then, so the name actually is not unique. You can have like, an audio interface and you have two of these, and you kind of connect both of them at the same time. Some operating systems say, fancy interface 1, fancy interface 2. Some operating systems will not do that, so you will have the same name for both of them. So what you want is also, you want like a unique ID type to distinguish them. All the APIs give you this kind of thing. And then you want to know whether the device is input or output, or maybe both, and how many input channels it has and how many output channels it has. Then you want to know what the sample rate is, and you want to know what the different sample rates are that this thing supports, and you want to set the sample rate. And then this is odd because on some operating systems, the native kind of sample rate, the native audio API uses double for the sample rate, and on others it's an int. So we just said, okay, let's say sample rate underscore t, because this is what you do in the standard library. So it's going to be some numeric type. And the same for the buffer size, which is the other parameter that you need to be able to control. What's your buffer size? Set the buffer size. What different buffer sizes do you support? That's it. And then you can start the device and stop it, and you can see if it's running. And that just means that it's going to actually call you back on these callbacks. And in the very early version of this, we had like an RII kind of thing where the device automatically starts when you create it and automatically stops when you kind of destroy it or when the destructors run. And it turned out like it's really nice RII, but it doesn't really work here because start actually means start calling me back on this callback. And sometimes you just want to do some setup before you do that. So if you want to connect to the device, and then say, okay, set the sample size to the sample rate to this, set the buffer size to this, do all this other setup in the user code, right? Not in the device class, and only then actually start producing stuff. So we want this kind of start and stop interface to be there, and then that's going to start calling you back on the audio callback, and the audio callback is just a function that takes a reference to the audio device because maybe you want to know which device called you, and then it takes this audio device buffers object, which I'm not sure yet about the name, but what it is, so you might have an input buffer or an output buffer or both, depending on whether it's an input device or an output device or both. And so it's just an optional input buffer and an optional output buffer. And you can have those as kind of two separate parameters to this callback, but then the kind of signature of the callback becomes long, and like this is one of the more interesting discussions we had on this email thread. So yeah, so we decided to go for this, and then unfortunately you can have different sample types and different buffer orderings. So we need to again template this thing on the sample type and on the buffer order. And then this is the most interesting function of this API, which means, so I have a callback. Let's connect it. And if you then do device start, it's going to start calling you back, calling this thing back on the audio thread. And this is where you can actually start doing stuff. And this is a template because the callback type is a template because first of all, it could be any callable, right? It could be a lambda, it could be a function, it could be a functor object, and then it could use some sample type and some buffer ordering, interleaved or de-interleaved. And you might want to use different ones. So what this is going to do is, if you're going to call it with a callback that requires, for example, float and interleaved, then this call is going to succeed if your native audio API supports float and interleaved, which most of them do. If you want, say, well, you want a de-interleaved int 128, then probably your hardware is not going to do that. So either it's going to succeed and then do the conversion out of the hood, or it will just fail. You cannot then connect this callback. And that really depends on the particular API, the particular implementation. So it's implementation defined. Like on an embedded platform, you might not be able to use float. So if you use a callback that wants a float sample type, this is not going to compile. And then, so talking about embedded. So you have certain APIs where it's basically this paradigm that I discussed earlier, where the operating system fabricates this high priority thread under the covers, and then it's going to call you back. And there's another way of doing it, which I heard from the gaming people, that this is more kind of how they think about this, is where you have like a pull-based API where you actually want to create the thread yourself and then say, okay, device, I'll wait until you have data for me, and then I'm gonna call you on my thread and do the processing. And then I'm gonna again wait until you have a new buffer for me and then call you and say, okay, give me this next buffer. So you end up in this like loop where you do wait, process, wait, process, wait, process, which is basically an alternative way of doing this. And that might not be possible on, oh yeah, and then you have also wait for and wait until, which is just another variation of this. And then this is interesting because on some operating systems, you can't really do this. Like, for example, on a Mac core audio, you don't have control over this audio thread. Like macOS just gives you, like creates a thread under the covers and gives you this thread, and this is not a thread that you can control. On Windows, Wasapi, for example, is the other way around. So you can kind of create this thread in the implementation of this, or you can just let the user control the thread. So you would have the option of do either connect or wait process. So we want to query this. Okay, can you do the connect thing where you just give me, you just call me back on your thread, or can you do the process thing? And then depending on, you can decide, which way of doing it you want. And then that's the device class. That's it. And then the only question left is, how do you obtain one of those devices? And so you need some kind of device discovery API. This is, I think, really straightforward. So you have a function that gives you the current default audio input device and the current default audio output device, which is optional because you might not have one. And this is what you will use most of the time. And you can also get a list of all the input devices and all the output devices, and that's just a list which you can iterate over. It's not really interesting. And this is how you get a device. So you can enumerate them, and you can use one of them, or you can just get the default. And then there's one last thing which is a bit unfortunate, which is, for example, if you take Ableton again, there's this driver type setting. So this is not going to be interesting for most people, but interestingly, some systems have more than one driver API that you can be talking to. So on Mac, you just have core audio, but on Windows, you have Wasapi and ACCU, and you can't just say, well, let's just use one of them, which is Wasapi is typically the default. 99% of the people are fine with that because you just want to play something, right? But if you're writing like high performance audio software, then it turns out that they have different trade-offs. Like for example, on Windows, Wasapi has more features, but then ACCU has lower latency. So you might actually want to choose which one to use and actually enumerate the different devices. So basically, Wasapi is going to be compatible with most of the stuff. In ASIO, there's going to be less devices that have an ASIO driver, but then those that do will have better latency. So you might want to enumerate the devices separately for these different driver types. And the confusing thing is that it's not really you can't really just type def, it can't be like a compiler flag or something, because you want to do this like at runtime. So in the same app, you want to do both, for example, Wasapi and ASIO on Windows. And the other thing that is useful is you want also to sometimes have a null driver, which just says, well, we just don't have any audio devices at all. And that's really useful, for example, in a system which just doesn't do any audio. And then you still, like, what you don't want to say, okay, then this part of the standard library doesn't apply to you. You want to just have something, and then the default driver is just this null driver. And this is also useful, like for testing. You have some kind of dummy driver which doesn't do anything but gives you this API basically. So how do we put this into this API? And so one way that I've seen in certain cross-platform audio middleware is that you kind of do this at runtime. There's like an inheritance thing, for example, or it's a thing where, okay, like give me the current input devices gets like an optional argument, and you can tell it, as a string, give me like Wasapi or whatever. So it doesn't really feel standardized. So we decided to do this kind of type-based system thing where we have these driver types as like little tag types. So the one thing that's always guaranteed to be there is the null driver. And then it's implementation defined which other driver types exist. Like on Mac, you would just have a core audio driver type, and then on Windows, you might have Wasapi driver type and ASIO driver type, and maybe on Android, you would also have several of those. And then there's another type def, which is always defined, which is the default driver. So again, basically the design goal here is that 99% of the users should never care about this and not even be aware of the fact that there are several drivers. But those people who do need that functionality. So it's this typical kind of API design challenge of make the stuff that most people use really easy and don't overburden them with like extra template parameters that they don't need. But if you need them, they are there. They're just a bit more ugly and a bit harder to find, but they are there. And this is pretty much the design goal here. So then the consequence of this is that unfortunately, and maybe there is a better way of doing this, I'm not sure yet, but unfortunately all these classes that we've seen, like device and device list, we need to make them templates on the driver type. And then basically there's this convenience type def, which is just the default driver thing. And then the same for the device list. And then the same for the device discovery API, which now kind of becomes, you will have one for each driver type. And I really like this. The one thing why I don't like this is that because the stuff becomes kind of really long. Like audio basic device list is, I think it's just a naming problem. I'm not sure this is the best name for it, but I think this is the right design. Oh yeah, one more thing is probably you want to convert between different types of buffers. So you want, for example, you have an algorithm that requires a de-interleaved buffer because you're doing some per channel stuff, and then the native one is the interleaved buffer. You want to just reorder it. It's basically just transposing a matrix. That's basically what it is. You want to have a convenience function for that, so we provide that. And live demo. So that's the part where it usually all goes wrong. But several things have already gone wrong today, so it can't get any worse than that. I think I have a few more minutes for that. So this is just the repository, which is online. Okay, so now, okay, I see. So now I have to stare at this screen and not at you. So otherwise, I don't see what I'm typing. And I also have to make it bigger. All right, so I have a few very simple example apps that show you this API that I just described. So this one, we just basically generate random numbers between -1 and 1 with this beautiful C++ standard random number API. I don't use the Mersenne Twister one because it's not real-time safe. I'm using this one, which is more appropriate because it's kind of less computationally expensive. And then what I do is I just generate these white noise. So basically, random samples is just white noise. So I just generate these random numbers, and I get the default device. If I don't have one, I just return. And then I do this connect callback, this connect call, and I give it an audio callback. And note that it's just a lambda now. So this is really, this all fits actually on one screen, which is not the case for any other API I have seen so far. And then you just start the device, and then you do this for 2 seconds, and then you shut down. So that's just going to play 2 seconds of white noise. Let's do that. Yep. So, yay. Oh, and this is really cool, by the way, I think. You can do that. And it's all in namespace still experimental at the moment because it's where not yet standardized stuff goes. All right, so the next one is a bit more complicated, but also just about fits on one screen, which is the sine wave one that I had on one of the slides, but just now with this API. So you kind of have to get the sample rate now, because if you want to have like a 440 hertz, which is the middle A, if you need to like figure out what you actually have to write, that depends on the sample rate. So you need to compute that, and then you just do this, which is not the optimal way of doing it, but it works. So you just generate the sine wave, and you kind of keep going, and then now you have to loop over the frames and the channels separately, because you want to write in each channel separately. You want to write the next number, and then if you do this, then it's going to output a 2-second sine wave. Next example, the melody, that's a bit more code. So what happens here is that we have an array with some note numbers, and then you have a little synthesizer which generates a square wave with this very, very inefficient way of generating a square wave. Square wave is just -1 to 1. That's like one of the typical ways you do like a very old kind of bit like 80s kind of gaming console things. They were all doing this, except more efficient than this. And then you kind of just like run through this array, and then there's like a MIDI note number, and you compute the pitch from that. It's not really interesting. And then what you do here is, so again, it depends on the sample rate, and then blah, 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 not really interesting. And then what you do is you just get the next sample from this very simple synthesizer, and you put that again into the output buffer, which is still about 90 lines of code. And if you play that, it's going to play a little melody. That's nice. So I can change it. Yeah, I don't think I have time to play around with this because you only have 5 minutes left. But you also get, oh, actually, that's the simplest one. That just literally just shows you what devices you currently have connected. So that's kind of using this device discovery API. So this is the output here. So I guess this is the thing that I'm running through now. This is the HDMI, and this is the built-in speakers. And you just print some like device properties here. And then the last one is the level meter. And that's a bit odd. I haven't really figured out why it doesn't work if I run it inside the debugger. So what I have to do here, so what it does is essentially it's a very crude way of estimating the volume of the input of the microphone. So what I have to do here is I have to actually run it in the terminal. I don't know why it doesn't work inside the debugger. Hang on, where is it? Sorry for that. Oh, here it is, the level meter. So this just displays the current volume, and if I do like you see it went up here. You see the numbers change, they go up. So this is just measuring, the very crude way of measuring the current volume of the audio input in 20 lines of code. So yeah, that's it, it works. We go back to the slides. So what next? So there's a few things that are missing in this API, which certainly the first one we need, which is, if you plug a device in or if you plug another one out, you need a callback for that as well, because if you're running through the speakers and then someone unplugs them, you want to detect that and switch to another output device. And it's a bit challenging because it's not really clear to us at the moment what a good way would be to have this kind of callback API that works very well with other cases in the standard library where you need such callbacks, because they should be kind of consistent, but we don't really have that in the standard library yet. So it becomes a problem of how do we do callbacks in C++, which a lot of people are thinking on at the moment. So let's see what comes out of that. So then coroutines are actually really useful here because, for example, with this example with the synth, which plays back the melody, you saw it's like a lot of boilerplate where you have like a struct that has some state and then it has like a call operator. And actually with coroutines, which we now have in C++ 20, yay, you can write this in half the code by just having a function, and then the state is just going to be the local variables of this function, and you just yield from the function whenever you generate a new value. It's like this kind of generator pattern. It's beautiful. Maybe we should kind of support this, but the open question is here, yeah, but how do you do input? So the generator thing is, yeah, it works with coroutines. How do you do the opposite, where you get input and you have to write this out? It's not clear yet to me how to do this with coroutines elegantly. So not sure yet whether we're going to use those. Clocks and timestamps, very important thing that we don't have yet. You might want to know if you get an audio buffer, when is it actually going to be playing back through your speakers, because then you can sync your audio to video or like events if you're in a game, if you do games. So this is important. But the challenge here is some APIs give you timestamps. On other systems, it is impossible to get a timestamp. So how do we do that? Maybe just add an optional timestamp to the callback. Not sure yet. Exclusive versus shared mode, we talked about this. Audio file I/O, I'm not really sure anymore whether we want to add this, to be honest, because you can do this once you have the low-level stuff in the standard library. You can do the rest on top of it in a portable way. So it would be nice to have a facility that, like we saw earlier, to just play back this file, but I'm not 100% sure we need it in the standard library. Because you can, if you have this in the standard library, you can build this on top of it. Maybe you want this. It's an active discussion going on. Let's see. And then MIDI is the other thing which is important for music makers, which is this other way of doing audio where you get MIDI events, MIDI notes, like from a keyboard. And there's another area that is not portably doable in C++ today, where you again have all these native APIs you have to talk to, or middleware, and so on and so forth. So maybe we want to add this as well. It kind of fits in very nicely. Not sure if it's general purpose enough. Certain things that are kind of out of scope for this API, not going to do this. Certain things like, are you allowed to access the microphone? Sometimes you get this dialogue, is like, do you allow the app to access the microphone? And this is, yeah, we're not going to do this. Like, I think the correct way of doing this is just provide the device discovery API, and if you want to connect to this device, then the implementation will probably pop up this dialogue. But it's not something that we would ever want to standardize. It's just too different in all these different platforms. Another one is audio focused, like for example. So what I talked about is really, really kind of obvious for desktop platforms. As soon as you get into mobile or embedded land, they do different things. So the question is, how much of this do we, and audio focus is a particular one where, let's say you have a player going on your phone and then someone calls you, and then that's going to override. So you're going to take the call, and then when you hang up, then it's going to jump back to the player app. So you have this kind of audio focus concept, which is important on phones. I don't think it belongs into the standard library. I think this is too different on all these platforms. Then they have proprietary spatial audio formats like Dolby Atmos, where you don't actually talk to a device. You don't write into a buffer of a device, you write into like an encoding stream, and then that encoding stream under the hood writes to the device, but you don't have to control over that. So yeah, this is also not reflected in this API. And then embedded is interesting because some of the stuff we designed here is supposed to work for embedded, but then I talked to some embedded people recently, and they're like, oh, no, this is not how we do. So I talked to an embedded person last week, and they were just looking at this API, and then they were saying, oh yeah, but we do this slightly different in embedded. And there was like this 10-minute monologue, which I didn't really understand, but the words interrupt and memory mapped device occurred very frequently in there. So I think embedded people do stuff differently. So it's an open question whether any of this is usable to them or not. Obviously, it's an important platform for C++. I don't know yet how to handle this. I'm not an embedded person. If you are, please talk to me. And then the other question is, where should this go? So now we have this library, we have this API. Should this go into a TS, like an audio TS, which is this kind of, not in the C++ standard, but kind of feature branch approach? Should it be an audio TS, or should it maybe be a human computer interface TS with audio and graphics in it? Should it go directly into the standard 23, 26? Should it just not go into this? Some people say this is out of scope for the standard library. So maybe it should become a boost audio thing. Maybe you should put it into boost. But you should do that anyway, by the way. You can have it there and in the standard library. Or maybe it's not a good fit in there either. Maybe it's just going to be another library. I don't know, but I hope it's going to be useful. And that's it. You can find me on Twitter. I have recently started a blog. You can find me on the Include CPP Discord. And yeah, if you find any of this interesting, or if you want to get involved, help us implement this on other platforms. Currently, it only works on macOS. Talk to us. Like, I'm here. Guy Davidson is here, who's the other co-author. The third one, Guy Somberg, is unfortunately not here, but we talk to each other. So talk to us, please. Help us. Let us know if it's useful. Let us know if some of the stuff is not good. Yeah, and that's it. Thank you.